Today, we will study a family of series methods for differential equations. The central idea is simple but powerful. Replace the unknown function by an infinite polynomial-like conveyor belt. Substitute it into the equation, align equal powers of x, and make every coefficient balance. Each balance creates information about the next coefficient. We will begin with the ordinary point method from your notes. Then extend the same pattern to Frobenius series, Legendre functions, Bessel functions, Hermite polynomials, and Laguerre polynomials. The notation may become longer, but the workflow stays recognizable. Green will mark a known coefficient or a completed step. Red will mark a mismatch that must be corrected. Purple will mark a recurrence or structural formula, and gold will highlight the conclusion. Keep one question in mind throughout. What is the lowest power, and what coefficient must vanish? Let us work through example 34. Exactly. We want a power series solution about x equals 0 for the equation 1 minus x squared y double prime minus 2xy prime plus 2dy equals 0. First, check the point. The coefficient of y double prime is 1 minus x squared. At x equals 0, it is 1, not 0, so 0 is an ordinary point. That is why an ordinary power series is appropriate. Y equals the sum from k equals 0 to infinity of a sub kx to the k. Differentiate term by term. The first derivative is the sum from k equals 0 to infinity of ka sub kx to the k minus 1. The second derivative is the sum from k equals 0 to infinity of a sub k times k minus 1 times x to the k minus 2. Substitute these three expressions into the differential equation. The factor 1 minus x squared splits the second derivative contribution into two sums. Combining the two terms already containing x to the k gives negative k squared plus k minus 2 times a sub k x to the k. The remaining sum begins at k equals 2. Replace its index by k plus 2. Then the coefficient of x to the k becomes k plus 2, k plus 1, a sub k plus 2, minus k squared plus k minus 2 a sub k. Setting that coefficient equal to 0 gives the recurrence a sub k plus 2 equals k minus 1 divided by k plus 1 times a sub k. Now we use the recurrence algorithmically. The two starting values, a sub 0 and a sub 1, are free because a second-order differential equation needs two independent constants. The recurrence advances by 2, so it creates two separate chains. Start with the even chain. At k equals 0, a sub 2 equals negative a sub 0. At k equals 2, a sub 4 equals 1/3 times a sub 2. So a sub 4 equals negative a sub 0 divided by 3. At k equals 4, a sub 6 equals 3 divided by 5 times a sub 4. So a sub 6 equals negative a sub 0 divided by 5. Notice that the coefficient changes as the chain continues. We must not assume every later coefficient is identical. For the odd chain, k equals 1 gives a sub 3 equal to 0. Then k equals 3 gives a sub 5 equal to 2 divided by 4 times 0, still 0. Every later odd coefficient is 0. Therefore, the solution begins y equals a sub 0 plus a sub 1x minus a sub 0 x squared minus a sub 0, divided by 3 times x to the 4th minus a sub 0 divided by 5 times x to the 6th, and so on. Equivalently, y equals a sub 0 times 1 minus x squared minus x to the 4th over 3 minus x to the 6th over 5, and so on, plus a sub 1x. The notes display the early terms as 1 minus x squared minus x to the 4th over 3, which is correct through that displayed order. The important structural lesson is that the recurrence separates parity. Even powers depend on a sub 0 and odd powers depend on a sub 1. The Frobenius method uses the same conveyor idea when the expansion point is a regular singular point rather than an ordinary point. Your notes use example 35. X times x minus 1 times y double prime, plus 3 times minus 1 times y prime, plus y equals 0, about x equals 0. Because the coefficient structure is singular at 0, we do not begin with ordinary powers alone. Instead, assume y equals the sum from k equals 0 to infinity of a sub k x to the power m plus k. Differentiating gives y prime equal to the sum of a sub k times m plus k times x to the power m plus k minus 1, and u double prime equal to the sum of a sub k times m plus k times m plus k minus 1 times x to the power m plus k minus 2. After substitution and collection, the lowest power is x to the power m minus 1. Its coefficient is negative a sub 0 times m squared. Since a sub 0 is not 0, the indicial equation is m squared equals 0. Thus, the repeated root is m equals 0, 0. The next power, x to the m, gives a sub 1 minus a sub 0 equals 0. So a sub 1 equals a sub 0. For a general power, the notes obtain a sub k times open bracket m plus k plus 2 plus 1 close bracket minus a sub k plus 1 times m plus k plus 1 squared equals 0. Substituting m equals 0 simplifies the bracket to k plus 1 squared. So a sub k plus 1 equals a sub k. Therefore, the displayed series is a sub 0 times 1 plus x squared plus x cubed, and so on. Because the indicial roots coincide, this calculation supplies only one solution. A second solution requires the repeated root theory. The Legendre differential equation in the notes is 1 minus x squared, y double prime minus 2xy prime plus n times n plus 1 times y equals 0. Its singular points are x equals plus or minus 1, while x equals 0 is ordinary. The notes develop a series with a symbolic leading exponent k. After substitution, compare the highest power x to the k. Its coefficient is a sub 0 times n minus k plus 1, so the possible values are k equals n or k equals negative n minus 1. The next lower power gives a sub 1 equal to 0, and therefore all odd-indexed coefficients vanish. Comparing the coefficient of x to the k minus r minus 2 produces the recurrence a sub r plus 2 equals divided by d k plus n minus r minus 1 times a sub r. For k equals n, this becomes a sub r plus 2 equals n minus r minus 1 divided by negative r plus 2, 2n minus r minus 1 times a sub r. At r equals 0, a sub 2 equals negative n times n minus 1 divided by 2 times 2n minus 1 times a sub 0. At r equals 2, a sub 4 equals n times n minus 1 times n minus 2 times n minus 3 divided by 2 times 4 times 2n minus 1 times 2n minus 3 times a sub 0. For non-negative integer n, this chain terminates and gives the Legendre polynomial p sub n. The other root, k equals negative n minus 1, gives a non-terminating branch called the Legendre function of the second kind, q sub n, in the notes. Rodrigues' formula packages the terminating branch neatly. P sub n of x equals 1 divided by 2 to the n times n factorial multiplied by the n derivative of x squared minus 1 to the n. Applying it gives p sub 0 of x equals 1, p sub 1 of x equals x, p sub 2 of x equals 1/2 times 3 times squared minus 1, and p sub 3 of x equals 1/2 times 5 times cubed minus 3 times. These formulas reveal several patterns. At x equals 1, every p sub n equals 1. At x equals negative 1, p sub n equals negative 1 to the n. Also, p sub n of negative x equals negative 1 to the n times p sub n of x. So even n gives an even function and odd n gives an odd function. The generating function is 1 minus 2xx plus z squared to the power negative 1/2 equal to the sum from n equals 0 to infinity of z to the n p sub n. Of x, the coefficient of z to the n is precisely p sub n. Setting z equal to 1 gives the useful identity that the sum of p sub n of x is 1 divided by the square root of 2 minus 2 times, wherever the series converges. Orthogonality is expressed by the integral from negative 1 to 1 of p sub n times pn dx equals 2 divided by 2n plus 1 times delta sub mn. Finally, the notes list recurrence relations, including np sub n equals 2n minus 1, xp sub n minus 1, p sub n minus 2. These relations let us move between neighboring polynomials without differentiating from scratch. The Bessel differential equation from the notes is x squared y double prime plus xy prime plus x squared minus n squared y equals 0. Here, x equals 0 is a regular singular point, so use y equal to the sum from r equals 0 to infinity of a sub r x to the power k plus r. Substitution and collection produce the sum of a sub r times x to the power k plus r plus the sum of a sub r x to the power k plus r plus 2 equal to 0. The lowest power gives a sub 0 times k squared minus n squared equals 0. Hence, k equals plus or minus n. The next power gives us sub 1 times equals 0, and the notes take a sub 1 equal to 0. Comparing the coefficient of x to the power k plus r plus 2 gives a sub r plus 2 times, plus a sub r equals 0. Therefore, a sub r plus 2 equals negative a sub r divided by k plus r plus 2 squared minus n squared. Choose k equals n. Then, a sub 2 equals negative a sub 0 divided by 2 squared times n plus 1. The next coefficient is a sub 4 equals a sub 0 divided by 2 to the 4th times 2 factorial times n plus 2. Thus, the series begins. A sub 0 times mand is dep when the grass is d squared in plus 1, plus x to the n plus 4 divided by 2 to the 4th times 2 factorial times n plus 1 times n plus 2, and so on. This non-terminating series is the Bessel function of the first kind, j sub n. The standard series form in the notes is j sub n of x equal to a sub 0 times the sum from r equals 0 to infinity of negative 1 to the r divided by r factorial times n plus r factorial multiplied by x over 2 to the power n plus 2r. For n equal to 0, j sub 0 begins 1 minus x squared divided by 2 squared plus x to the 4th divided by 2 squared times 4 squared minus x to the 6th divided by 2 squared times 4 squared times 6 squared, and so on. For n equal to 1, j sub 1 begins x over 2 minus x cubed divided by 2 squared times 4 plus x to the 5th divided by 2 squared times 4 squared times 6, and so on. The graph shows oscillations with changing apparent period and decreasing amplitude. J sub 0 starts at 1, while j sub 1 starts at 0. The notes list the first zeros of j sub 0 near 2.4048 and 5.5201, and of j sub 1 near 3.8317 and 7.015. Even order gives an even function, and odd order gives an odd function. Useful special cases are j sub 1/2 of x equals the square root of 2 divided by pi x times sine x, and j sub negative 1/2 of x equals the same square root times cosine x. The recurrence relations include xj sub n prime equals njn minus xjn plus 1. 2j sub n prime equals j sub n minus 1 minus j sub n plus 1. And 2njn equals x times open parenthesis j sub n minus 1 plus j sub n plus 1 close parenthesis. The generating function is the exponential of x over 2 times open parenthesis z minus 1 over z, close parenthesis, equal to the sum from n equals negative infinity to infinity of z to the n j sub n of x. The Hermite differential equation in the notes is y double prime minus 2xy prime plus 2ny equals 0, and x equals 0 is an ordinary point. Use y equal to the sum from r equals 0 to infinity of a sub r x to the power k plus r. Substitution gives a first contribution with x to the power k plus r minus 2, and a second contribution with x to the power k plus r. The lowest power produces a sub 0 times k minus 1 equals 0, so k equals 0 or k equals 1. The next power gives us sub 1 times k plus 1 times k equals 0. For the general power, the notes obtain a sub r plus 2 times k plus r plus 2, k plus r plus 1 minus 2a sub r times k plus r minus n equals 0. Thus, a sub r plus 2 equals 2 times k plus r minus n divided by k plus r plus 2, k plus r plus 1 times a sub r. For k equals 0, the even chain begins a sub 2 equals negative 2n divided by 2 factorial times a sub 0, and a sub 4 equals 2 squared n times n minus 2 divided by 4 factorial times a sub 0. The odd chain begins with a sub 1 and gives a sub 3 equal to negative 2 times n minus 1 divided by 3 factorial times a sub 1, followed by a sub 5 equal to 2 squared times n minus 1 times n minus 3, divided by 5 factorial times a sub 1. Therefore, the general solution is a times y sub 1 plus b times y sub 2, one even type series and one odd type series. When n is a suitable non-negative integer, one chain terminates and becomes a Hermite polynomial. The recurrence has done the same job as before. It separates parity and controls every later coefficient. For even n, the Hermite series terminates and the notes write the polynomial as h sub n of x equal to the sum from r equals 0 to n over 2 of negative 1 to the r times n factorial divided by r factorial times n minus 2r factorial, multiplied by 2 times to the power n minus 2r. Rodriguez' formula is h sub n of x equals negative 1 to the n times e to the x squared times the nth derivative of e to the negative x squared. The first examples are h sub 0 equals 1, h sub 1 equals 2 times, h sub 2 equals 4 times squared minus 2, h sub 3 equals 8 times cubed, and h sub 4 equals 16 times to the fourth minus 48 times squared plus 12. These immediately show the parity rule. H sub n of negative x equals negative 1 to the n h sub n of x. The generating function is e to the power 2xx minus z squared equal to the sum from n equals 0 to infinity of h sub n of x divided by n factorial times z to the n. Therefore, the coefficient of z to the n is h sub n divided by n factorial. Your orthogonality relation uses the Gaussian weight. The integral from negative infinity to infinity of e to the negative x squared h sub n dx equals 2 to the n times n factorial times the square root of pi times delta sub mn. The notes also list h sub n prime equals 2n h sub n minus 1 and 2x h sub n equals 2n h sub n minus 1 plus h sub n plus 1. These are not isolated facts. The differential equation, generating function, derivative relation, and orthogonality all describe the same polynomial family from different viewpoints. The Laguerre differential equation in the notes is xy double prime plus 1 minus x y prime plus ny equals 0. The point x equals 0 is a regular singular point. Assume y equals the sum from r equals 0 to infinity of a sub r x to the power k plus r. After substitution, the collected expression is the sum of a sub r times k plus r squared x to the power k plus r minus 1 minus the sum of a sub r times k plus r minus n x to the power k plus r equal to 0. The lowest power x to the k minus 1 gives a sub 0 k squared equals 0. Since a sub 0 is non-zero, the repeated indicial root is k equals 0. Equating the coefficient of the general power gives a sub r plus 1 times k plus r plus 1 squared minus a sub r times k plus r minus n equals 0. With k equal to 0, the recurrence is a sub r plus 1 equals r minus n divided by r plus 1 squared times a sub r. Compute the first terms. A sub 1 equals negative n a sub 0. Next, a sub 2 equals 1 minus n divided by 2 squared times a sub 1, which equals positive n times n minus 1 divided by 2 factorial, squared times a sub 0. Then a sub 3 equals 2 minus n divided by 3 squared times a sub 2, giving negative n times n minus 1 times n minus 2, divided by 3 factorial squared times a sub 0. In general, a sub r equals negative 1 to the r times n factorial, divided by n minus r factorial times r factorial squared, times a sub 0. For non-negative integer n, the series terminates. Rodriguez's formula is L sub n of x equals e to the x divided by n factorial times the nth derivative of x to the n e to the negative x. The first examples are L sub 0 equals 1, L sub 1 equals 1 minus x, L sub 2 equals 1/2 times x squared minus 4 times plus 2, and L sub 3 equals 1/6 times negative x cubed plus 9 times squared minus 18 times plus 6. The notes emphasize that these polynomial families are useful partly because different degrees can be separated by integration. For Legendre polynomials, the orthogonality formula is the integral from negative 1 to 1 of p sub m of x times p sub n of x dx equals 2 divided by 2n plus 1 times delta sub mn. The Kronecker delta is 0 when the degrees differ and 1 when they match. So distinct Legendre polynomials are perpendicular under this integral pairing. For Laguerre polynomials, the corresponding weighted relation is the integral from 0 to infinity of e to the negative xl sub n of x dx equals delta sub mn. The exponential is the weight that makes the family orthogonal on the half-line. For Hermite polynomials, the weight is e to the negative x squared, and the integral from negative infinity to infinity of e to the negative x squared h sub n of x hm of x dx equals 2 to the n times n factorial times the square root of pi times delta sub mn. The Bessel notes give an orthonormality condition involving the integral from 0 to 1 of xj sub n of alpha x j sub n of beta x dx. Its value is 0 when the parameters are distinct, and when they match, it involves 1/2 times jn plus 1 of alpha squared. The big idea is that a weight and an interval define the measuring device. Orthogonality is not merely a decorative identity, it lets us extract coefficients when approximating a function by a series of these basis functions. Let us apply the ideas to the 2 previous year questions in the notes. First, suppose polynomials are orthonormal on the interval from 2 to 4. A constant normalized polynomial p sub 0 must satisfy the integral from 2 to 4 of p sub 0 squared dx equals 1. If p sub 0 is the constant n, then n squared times the interval length 2 equals 1. So n equals 1 over the square root of 2. For a first-degree polynomial, choose p sub 1 equal to square root of 3 divided by square root of 2 times 3 minus x. It is orthogonal to p sub 0 because the integral from 2 to 4 of 3 minus x dx is 0. An antiderivative is 3 times minus x squared divided by 2, and its endpoint difference is 12 minus 8, minus 6 minus 2, which is 4 minus 4, or 0. Therefore, the matching option is the one with p sub 0 equal to 1 over square root of 2, and p sub 1 equal to square root of 3 over square root of 2 times 3 minus x. The second question gives the Legendre generating function 1 minus 2xt plus t squared to the power negative 1/2 and asks for p sub 3 of negative 1. We already know the endpoint rule p sub n of negative 1 equals negative 1 to the n. Therefore, p sub 3 of negative 1 equals negative 1, which is the correct choice. Notice how the first problem uses normalization and orthogonality directly, while the second uses a structural property extracted from the generating function family. Let us assemble the method into a reusable checklist. First, inspect the expansion point. If the leading coefficient is non-zero there, use an ordinary power series with integer powers. If the point is regular singular, use a Frobenius series with an unknown exponent. Second, write the assumed series and differentiate carefully, keeping summation limits visible and giving the sums generous vertical space. Third, substitute every expression into the differential equation. Fourth, rewrite every contribution using the same power of x. This index alignment is the heart of the method. Fifth, set the coefficient of the lowest power equal to 0. That gives an indicial equation when the point is singular, or it starts the coefficient comparison at an ordinary point. Sixth, equate a general coefficient to 0 and solve for the next coefficient. A step of 2 creates even and odd chains. A step of 1 creates a single consecutive chain. Seventh, calculate at least several coefficients by hand to catch an index or sign error. Finally, identify the resulting family: Legendre, Bessel, Hermite, or Laguerre when the recurrence and normalization match. The worked ordinary point example illustrated the entire conveyor. Substitute, align, equate, recur, and split into 2 chains. The special function sections repeat that same logic while changing the differential equation, the starting exponent, and the useful interpretation. You can now read a power series solution as an organized conversation between powers and coefficients. At an ordinary point, start with the sum of a sub kx to the k. At a regular singular point, allow the leading exponent to be m or k, and let the lowest power determine the indicial equation. In example 34, the recurrence was a sub k plus 2 equals k minus 1 divided by k plus 1 times a sub k. It immediately showed that a sub 2 equals negative a sub 0, a sub 3 equals 0, a sub 4 equals negative a sub 0 divided by 3, and a sub 5 equals 0. The even and odd chains explain why 2 arbitrary constants appear. Frobenius analysis explains repeated roots. Legend series terminate for suitable integer degrees and satisfy endpoint, parity, generating function, recurrence, and orthogonality identities. Bessel series produce oscillatory functions with decreasing amplitude. Hermite and Laguerre recurrences produce polynomial families with their own parity, generating, Rodrigues, and weighted orthogonality formulas. When solving a new problem, do not memorize disconnected formulas first. Rebuild the conveyor, choose the series, substitute align powers, equate coefficients, and verify the first terms. That algorithm is the reliable path from a differential equation to its series solution.